very much for the introduction and for the invitation. So I'm going to talk about a work joined with Marian Pirashvili, Lee Steinberg, Jeremy Frey, and Jacek Brodsky. So this is the plan for my talk. So I'm going to start giving a motivation and the background. Then I'm going to talk about geometric models for molecules and conformational spaces. And in the last part of the talk, I will give some results about data-driven approaches to conformational spaces. So let's start. So first of all, why do we want to study conformational spaces? So just let me recall that the potential energy surface of a molecule is defined on its conformational space. And the identification of energetically favorable conformers is fundamental in molecular physics and computational chemistry. For instance, the problem of protein folding is sometimes stated as an optimization problem, so of minimizing the potential energy function on a high dimensional space. In this case, this high dimensional space will be the conformational space of the protein. Another reason to study conformational spaces is to understand the binding pose of and strength of a drug with its potential target. So for that, we need to study the energy landscape of the drug. And as we said, this is defined on its conformational space. And well, here I'm just putting maybe a very well-known molecule. So if we think of these green spheres as carbon atoms and the blue spheres as hydrogen. So this is just the ethane molecule. And well, here we have that we know that there are two special conformations, which are the eclipsed one and the staggered. However, if we allow rotations, allow this bond, indeed we will realize that there are not only two conformations, but there are plenty of them. And the studies, well, the idea is to study what the topology of the space in which these conformations live is. So let's start then with a bit of background now. Oh, sorry, before that. Okay, so how can we model the space of all possible three-dimensional arrangement? This is the first question. And another question is, what conformations are related by a transformation of a group of symmetries of a molecule? So for instance, what these questions are important? Well, the quantum mechanical description of a molecular system, we know that must be invariant to any of the following transformations. For instance, if I rotate the position of particles about any axis, through the center of mass, any conformation that I have doing this operation should be equivalent. Well, these two conformations would be equivalent physically and chemically. So we need to kind of get rid of these transformations to avoid duplications of conformers. Also, we need to get rid of translations because, again, having a conformer in a space, in a particular point in the space should be the same if we translate that conformation to another point. Another thing that we need to get rid of, or we need to consider here, is the permutation of the positions of any set of identical nuclei, and the simultaneous inversion of position of all particles in the center of mass. We are going to talk about this with more details in a few slides later. All right, so let me say a bit of the background now on conformational spaces. So the simplest model that we can think of for a conformational space is the configuration space of endpoints in R3. So basically, this is the set of n tuples in R3 to the n, satisfying the condition that any of these tuples can be repeated. So here, xi and xj cannot be the same if I and j are the same. So we can have all these, any kind of position of this. For instance, in this figure, I have some atoms. And so this will represent, for instance, a very simple model for a molecule. It's just these atoms or these points. And they can live wherever, but the only condition is that they do not coincide in the same, they are not in the same place. So this was the model that Guichard adopted in 1984. And well, so the only restriction that he imposed in this construction was that he didn't allow any collinear configuration. That means that if we have endpoints, these endpoints cannot live all of the same, cannot be collinear at the same time. So also he considered conformations equivalent if they were related by either a translation or a rotation or a combination of translations and rotations. But in this model, for instance, he did not consider permutations of similar points. In this case, for instance, he didn't consider either the labels of the types of atoms. However, well, in this case, for instance, because these particles will be indistinguishable, and we should be careful, well, we should care about getting rid of all the permutations in which we are just well, all the configurations that differ by just a permutation of the labels of the atoms. Well, this is just a bit of the theoretical part and was done in, 1984, but more recently, in 2010, Martin and others study methods, use methods of algebraic geometry and topological data analysis to study the conformational space of cyclooctane. So here I'm just putting three conformers of cyclooctane. And well, one of the interesting results about this work is that usually people thought that the conformational spaces of molecules needed to be a manifold. However, he showed that it is not the case, for instance, for the molecule of cyclooctane. So using TDA, or topological data analysis, he showed that indeed this is the shape of this, the conformational space is described as the Klein bottle, which is inside in this figure. So the part inside of this kind of a sphere around that shape is a Klein bottle, and this is intersecting with a sphere in two circles. So here there are two circles in which these there are intersections of these manifolds, which are the Klein bottle and the sphere. So that means that at any point, in any neighborhood about a point in one of these intersections is not locally similar to a Euclidean space. So therefore, it cannot be a manifold. So somehow this was a very interesting result. So people started thinking that maybe we needed to analyze with more details these conformational spaces. And one of the ideas was to use the recently new tool of data analysis, TDA. All right, so having all this background in mind, let's start with the second part of the talk, which is trying to construct a geometric model for molecules and their conformational spaces. Okay, so first of all, I would like to say that this geometric model, I'm going to start trying to give a model for molecules and for conformers, and building up with on this, I'm going to say something about the conformational spaces. So we are going to model a molecule by a molecular graph. So the molecular graph consists of the following data. So we will start with a graph, which is formed by a set of vertices P with n elements, for instance, which will be our atoms in this case, and a set of edges, which is basically formed by pairs of atoms. And this will represent our bonds in our molecule. Then we will have a function C sub P from the set of vertices to R. And this function basically will define the atomic mass of the atom. So basically with that, we are kind of labeling these vertices by the type of atom that we have in our model. Then we will have another function L, which will define the bond lengths. And finally, we will have a function theta, which well, here maybe it's a bit of a technical definition for this set, but basically this is the set of all angles between bonds. And well, of course, that if we take for each element in the set of edges, we take a segment of line having a length equal to the bond length associated to this edge, and we glue it in the obvious way, so in the way that our graph is telling us, then we will obtain what we call a geometric realization of our molecular graph. So this basically defines a molecule not just as a combinatorial object, but as a geometric object. And well, one of the things that we have, I want you to notice is that this model basically is using a kind of a rigidity hypothesis. That means that these three properties that we are adding to the molecular graph, 3 and 4, these two properties, basically we are fixing the bond of the length of the bonds, and we are fixing the angles, which in many cases is not very, it's not not that bad to consider. So for instance, in organic molecules, we know that the variation of bond lengths might be very small and similar for the angles between bonds. So we are using this rigidity hypothesis in our construction. All right, so now we have here then a comparison between these two models. For instance, in the Guichard-Debs model, we have just points. And well, in here, I added a label to these points according to the type of atom. So here is a molecular models for one propanol. So in this case, the set of edges is empty, and therefore also all the other functions might not be defined either. So here we just have vertices, and all the vertices have associated the type of atom. And in the more kind of like a realistic model, then we will have atoms which are joined depending on the structure of the molecule that can be given in different ways by chemists. And then also we are associating the colors, the type of colors to them. And of course, well, here, although I have only a two-dimensional representation of this construction, but here, well, obviously we don't have to forget that there are some angles associated to pairs of bonds, and also bond lengths associated to each of the edges. Okay, so what is then a conformation? So a molecular conformation, or conformer of a molecular graph M, is just an injective function from our geometric realization of M into R3, and such that I have the following properties. First, this function has to preserve the length of the bonds, and also it has to preserve the angles between bonds. And well, I mean, maybe a best or a better way to think about a conformational conformer is not just as a function, but maybe as the image of the vertices under that function. So for instance, here, a conformer phi can be indeed represented by a tuple of points in 3 to the n. And here the vertices basically are given by these points, the images of the elements in the set of vertices under the function phi. Okay, so the conformational space of a molecular graph M is then the set of all conformers of the molecular graph M. And well, here again, I took two representatives or two elements that living in this conformational space for the case of the, when M is our molecular graph represents the ethane. And these are two, the typical two or special configurations or conformations, which are the eclipsed one and the staggered one. However, we know that there are many, many other conformations living in this space. Okay, so given now a molecular graph, well, we know that there are several symmetries associated to them. So again, we need to consider in chemistry, it's important also to consider to the symmetries associated to the molecule, for this reason related to the quantum mechanics description. So now we will try to say something about what happened, for instance, with the how to define symmetries of molecular graphs that are, say, not rigid in the sense that we have, for instance, in an ethane, and we will have maybe depending on the conformer, we might have associated different point groups. So in this case, for ethane, depending on the conformer, the point groups will differ, but maybe there is another way in which we can kind of combine these notions in one go. So, so then a molecular graph permutation is just a bijection in the set of vertices which satisfy the following properties. The vertices of an edge must go to the vertices of an edge under the permutation, and also it preserves the of atoms, the bond lengths, the angles between bonds, and the other, well, which are basically given by these functions. And well, here in these pictures, I'm just trying to represent what a molecular graph permutation is and what a molecular graph permutation is not. And so if I start, for instance, with this conformation, so I can put a label, arbitrary label, and then I can apply a permutation, which is just like swapping the labels associated to each of these vertices. So for instance, in this case, if I swap the right-hand side with the methyls in the propane, then we will have a molecular graph permutation. Why it is a molecular graph permutation? Well, we can see is that, for instance, in this case, the atoms in the positions 1 and 3 have a valency degree of 3, so it preserves kind of the valency under the permutation. Also, we are swapping carbons, and also in the case of the hydrogens, we are just exchanging hydrogens to hydrogens. And of course, the geometry around this carbon is preserved under this permutation. What is not a permutation, a molecular graph permutation, is this other, because in this case, so for instance, we have for the original, our initial atom labeled with number 2, we have, it was adjacent to the vertices 1, 3, 8, and 7, whereas in this new conformation, 2 is adjacent to 4, 5, 6, and 1. So this is not a molecular graph permutation. Okay, so these transformations, what is interesting about this transformation is that they preserve the topology of the underlying graph. And also, because of these constraints, the angle constraints that we are imposing, this permutation also must preserve the rigidity of the bond angles. Maybe here we cannot see it, but we need to define other functions to see how this permutation must preserve this rigidity of the angles between bonds. Okay, so our rigidity assumption and on our molecular model give rise to orientations around any non-planar atom. So we think about planar atoms as atoms with are attached to all the neighborhood around that atom lies on a plane. Yeah, so for instance, in this case, we have these 3 examples of planar atoms. All of them lie on a plane, and these are examples of non-planar atoms. So a typical example is, for instance, all the carbon with a hybridization sp3, and then we have this example of a non-planar atom. Okay, so the orientation of an embedding is just as kind of this is given by this definition. So it's a map from the triples of vertices, which are adjacent. So for instance, I can take here a triple of vertex. And basically the idea of giving an orientation is that once we have defined the label of we have given a label to each of the vertices, a numbering, say, we need to choose either the right hand rule or the left hand rule, and then decide an orientation according to the one of these two rules for this of edges. So basically we think here, so in this definition is that these differences are defining vectors that go along the edges of the of a given in the molecule. And here basically we are taking a cross product and a dot product, and then we only take the sign of the value of doing these operations here. And the sign function is just depending on the value, if the number here is less than 0, then it's -1. If c is equal to 0, then it's 0. And if c is bigger than 0, then the sign is 1. So here I just have to notice that when we have a planar atom, for instance, like in here, then the sign will be 0. So we are interested in things which are not planar. Okay, so a graph permutation is orientation preserving if after applying our operation to G to these vertices, then the orientation is doesn't change for every triple of every triple of edges which are adjacent. And we say that it is orientation reversing if when we apply this permutation to this triple of vertices, the sign of the orientation changes for every of the triple of vertices in our molecule. So here I'm have to give some examples of orientation reversing and orientation preserving. So here, for instance, this is a orientation preserving when we start with this conformation and we have this labeling, and then if we do some permutations, for instance, in here we are just kind of swapping this methyl from one side to another side, and we just are swapping these two vertices, these two hydrogens, then we will have that this is orientation preserving. And something that is not, which is orientation reversing is this other permutation, in which basically what we do here is just we took a mirror reflection through the symmetry, a plane of symmetry in this molecule, and then we just reflect the molecule, and then we obtain this other conformation or labeling for the conformation. Okay, so the antipodal map is the function that simultaneously inverts the position of all atoms in the center of mass. So for instance, we have again this conformation. Our center of mass will be about here, more or less around here. And then if we invert all the coordinates of the atoms, what we will obtain is this other conformation. Okay, and so we define the graph permutation inversion group for a given molecule as the set of all graph permutations of a molecular graph that either preserve the orientations around all non-planar atoms or preserve them after composition with the antipodal maps. So as I said at the beginning, I just defined a graph permutation of a molecular graph without considering the orientations, but here to define the group of symmetries that's some kind of take into account these permutations of identical nuclei, we restricted to those that preserve the orientation. And this is very important in chemistry, because if we included some other kind of permutations, then what is happening is that at some point we will need to go through a planar conformation, which is not allowed in our model. And in general, in chemistry, we know that, for instance, going through basically is a plane. For instance, if we want to swap only these two atoms, we would need to go through a planar conformation, which would be energetically not very favorable. So for these kind of molecules, which are kind of rigid in terms of the angles, we needed to restrict to these kind of permutations. Okay, so now I'm just giving some examples of these molecular graphs and the associated GPI group for short. And here I'm comparing against what is called the CMPI group. So this CMPI group is was basically defined for a model similar to the one defined for Guichardet. But in this case, all the possible permutations are allowed between atoms which are identically the same. So that means that this group is huge, and indeed is bigger than this one, because for GPI, we are not allowed in all the kind of permutation, but the ones that only preserve the orientation of the atoms. And here, for instance, the size of this group is as n factorial times, in this case, 2, whereas which increases very quickly with increasing the number n. And in this case, the size of these are much smaller, so we kind of handle much better these kind of groups. And also, but this is not the most important thing. The important thing is that we are respecting the topology of the underlying molecular graph, which is very important. So we know that we cannot go through very energetically disfavorable conformations, because of the topology is kind of constrained by the angles that we are defining between bonds. And so, yeah, so these are kind of some of the examples that we can have. So for instance, we have pentane. Pentane is, for the CMPI group, the size is n 5 factorial times 12 factorial times 2, whereas in this case, the size is 3 times 2 times 2. So it's a much smaller group. And also, again, it considers the, it preserves the topology and the constraints and the angles. Okay, so now, well, but this is just only on the side of molecular graphs. Now we need to relate it to conformational spaces of the molecule. So what are the symmetries associated to the conformational spaces? All right, so far we have seen that the group of rigid rotations in the Euclidean space is a group of transformations of its conformational space. And this operates by translation on a molecule, so it will induce an operation on the conformational space. And also, the group of rigid body rotations operates on by rotation of a molecule, which induces an operation in the conformational space. And the graph permutation inversion group operates by, again, permuting atoms. So all of these three operations will be involved, or will be somehow adding extra or kind of a duplicating conformers. So at some point we might need to get rid of all these duplications of conformers, and for that we need to kind of take into account this group of symmetries. So now basically the fact that we have different symmetries acting or transforming the space of conformers, so we might have different notions of conformational spaces depending on what kind of symmetry actions we are getting rid of. So for instance, if we get rid of the all the transformations that translate conformers, then we will have this new conformational space called CP. Then if we get rid of rotations and translations, we obtain what is called in physics and chemistry, the internal conformational space. And additionally, if we get rid of all the rotations, translation, and the all the permutations of atoms, which preserve the orientation in this case, then we obtain what is called the internal conformational space. And to all of them, we can associate a metric. So far we had said that, well, these are just sets of molecular graphs or conformation of molecular graphs, but we can endow these sets with a metric, and depending on which type of conformational space, the metric will be different. So for instance, in this case, for CP, the metric is so if X and Y are two conformers, then the metric or the distance between these two conformers is defined as where this norm is just the Frobenius norm. So basically X and Y can be two conformations, and these conformations again are represented as matrices of size 3 times n, sorry. Okay. And now in the case of the Procrustes, the conformations of the internal configurational space, the distance is given by the Procrustes distance. So we take the infimum over all these norms, and here R varies on, takes values in the elements of the matrices SO3s. This is the set of matrices that act by rotation. And in this case, also we have a similar definition for a distance for the case of the orbifold conformational space, in which basically here this G dot Y means the we take Y and then we apply the function defined by G, which lives in the group of symmetries GPI, the graph permutation inversion group. All right, so far this is what we did for to describe the theory and how can this molecular graphs notion will give rise to different ways to define conformational spaces depending on the symmetries that we are taking into account. We can define metrics, and now how can we study the topology of these conformational spaces? Well, one way to do it is also to use the tools from topological data analysis. So our goal in this part of our project was to analyze the topological features of the conformational spaces, well, of two conformational spaces. One is the internal configurational space and the other is the orbifold configurational space. And also we wanted to analyze their energy landscapes using tools from TDA. For that, we generate sets of 10,000 conformers of small molecules like butane, pentane, fluoropentane, and alanine dipeptide, which was our benchmark molecule. And here I'm just showing the figure, well, a picture of this alanine dipeptide. So basically, this molecule has a kind of is allowed to rotate along this bond and along this other bond, which basically these constraints basically define how the topology, the conformational space looks like. And also we use the data set of Cyclooctane of the work of Martin and others. And additionally to this, obtaining the set of the conformers for the given molecules, we calculate the potential energies of each of these conformers. And this was in order to obtain, to study the energy landscapes of the molecules, and well, to study both the energy landscapes and the conformational space, you will use different data analytical tools like Procrustes analysis, local PCA, or local principal component analysis, persistent homology, and discrete Morse theory. First, we wanted to study the topology of the internal configurational space. So for that, again, as I mentioned before, the metric is defined by the Procrustes metric. And given, for instance, a set of conformations, we use the MATLAB function Procrustes. And with that, we try to reconstruct the the conformational space, the internal conformational space. So the resulting topological space was embedded into a Euclidean space, high dimensional, and projected then to 3-dimensional. And are the pictures that I'm showing in here. So for instance, in the case of butane, we see that the conformational space is just a circle. It's a bit like distorted, but topologically it is a circle and looks like a circle. And in the case of the alanine dipeptide, so here it looks like a tori. And so these two pictures coincide what we were expecting. However, this is not maybe it's not enough to conclusively say that these are the shapes of our data. So we needed to do extra analysis to check the topological properties of these spaces. So then, as I mentioned, some people, for instance, tend to use a local principal component analysis because so principal component analysis is a method that tells us what is the minimum, the dimension of the minimum dimension of a linear space in which our topological space or geometric space can be embedded into. So somehow in some cases it is confused that people think that the dimensions that the principal components that we obtain there is going to tell us about the dimension of our space, which is not always the case. For instance, in maths, it's well known that for instance, for spaces which are not orientable, the minimum dimension to embed it into an Euclidean space or linear space is 2 times n, where n is the dimension of the space. So in this case, for instance, we could see 2 to the n principal components, but the dimension of the space is not 2n, but n. So so somehow is we get bounds on the dimension of our space, but this is not an optimum bound. So local PCA, on the other hand, gives us a much accurate result in terms of the dimension of our topological space. So we try to do that. So we basically, what we do is we study a point, we study a neighborhood about any point in our topological space, and we study the dimension which of the Euclidean space, which can be isomorphic to this neighborhood about that point. And so, so somehow, in order to do this, we basically, given a conformer, we computed its k nearest neighbors, and we obtain using local PCA or principal component analysis, we obtain a linear approximation of this neighborhood. And then we modify the algorithm given by Singer and others to test orientability of the internal configurational space and the orbifold configurational space. So basically, this algorithm says that if a space is orientable, so there are only 2 possibilities of orientations for each of the neighborhoods. And so that means that, again, we would see in this kind of plots that, so here is we are just kind of getting all the plotting what are these orientations for every neighborhood of a point are. And so these are two possibilities. Either is negative or positive, and both coincide in absolute value. So here, for instance, for alanine dipeptide, we see that there are clearly these two possibilities. But in the case when something is non-orientable, the algorithm cannot have something only two possibilities, but something which some other lines will appear in the middle, saying that the algorithm cannot define exactly what the orientation is. So in the case of the alanine dipeptide, we obtained that these are this is an orientable space, which is again because this is our benchmark molecule. We knew exactly what to expect, which coincides with what we have. And then for pentane, we also get that even though there is a bit of noise, there are also two regions in which that separates the types of orientations that have. But in the case of the orbifold configurational space of pentane, the orientability, our orientability algorithm is showing that this is not an orientable space. So then, of course, here we are looking at a crucial difference. So if two spaces are if one space is non-orientable and the other is orientable, then topologically these are different. So then we can see that the internal configurational space and the configurational space that we obtain when we get rid of all the possible permutations of the molecule are not topologically equivalent. All right, so in the case of the data set obtained by Martin and others, of course, first of all, this algorithm of orientability is supposed to be used in a data point sample from manifolds. So we knew that the data set, the original data set of Martin and others was not a manifold, but still, we try to see what the algorithm showed, and this indeed basically is saying that so the algorithm cannot say anything about it's kind of finding that it's not orientable at least. Then what we try to do is to split the data into two clusters. And what we obtain is that these two clusters, one of them is orientable, clearly orientable, whereas the other is not. So because we knew from this paper of Martin that one corresponds to the sphere, which is the orientable case, and the other corresponds to the Klein bottle, which is a non-orientable surface. Besides, of doing all this analysis, we also carried out computations of persistent homology. So Jacek somehow give an introduction to persistent homology, in which we already have seen that, in this case, we want to count the number of disconnected pieces that a space has, or number of holes or voids of higher dimensional analogs. So these are counted by the Betti numbers, which are denoted beta I. So beta 0 is the Betti number that counts the number of holes, the number of disconnected pieces. Beta 1 counts the number of holes, and beta 2 counts the number of voids. And similarly for higher dimensional analogs. So this computation were carried out in Ripser. So this is a open software. And so here I'm just showing the persistent diagram associated to the alanine dipeptide. And what we have is that we have that alanine dipeptide, the topology is given by a Taurus. And we know from the theory that it must have one connected component, two holes, and one void. And this is precisely what we are finding in this this persistent diagram. So these the black dots correspond to the disconnected pieces. Oh, the connected pieces here, it corresponds, the red dots correspond to the holes, and the blue dots correspond to the voids. And now we check again with persistent homology, the topology, for instance, of pentane. And pentane, again, is the topology of pentane is seems to be like a torus. So we have one connected component, two holes, and one void. But when we study the orbifold configurational space of pentane, we already see that the topology has changed. Now we have only one connected component and only one circle, and the void has disappeared. So with that, we confirm that these two spaces are not topologically equivalent. And well, indeed, with this kind of construction, theoretical construction of having this kind of a torus depicted in this way. So we identify, if we have a piece of paper and we glue these two edges and these two other edges, what we obtain is a torus. And now what we do with this, the graph permutation inversion group, which is consists of two elements. We just kind of identify these 2 points. So basically we kind of fold this square along this diagonal. And what we obtain is something that looks like a Möbius band. And this indeed, this persistent diagram coincides with what the theory tells us. Okay, so now in the case of cyclooctane, again, we obtain the persistent homology for each of the, either for all the set, for when we split into clusters, and what we can see is that the topology of these spaces is different, clearly different. And well, I have here a quick characterization of these properties. So here, local dimension, number of singularities, if it is orientable node or not, and the Betty numbers. And well, just briefly, just to finish, let me take 1 minute or more to say something about the energy landscapes. So basically, an energy landscape, again, is a function defined on the and the configurational space or the conformational space. In this case, usually people think of it as defined over the internal configurational space. And well, these force fields contain parameters describing the relative strength of bonds, and the stretching of bonds, torsional rotation within a molecule. And we use discrete Morse theory to analyze the potential energy surface or energy landscapes. And also we use a topological tool, which is available to use. And well, here I'm just showing what we obtain. So for instance, so the idea was to use Morse theory. Is similar to what Jacek described, in which we take a function and we do a filtration, a high filtration, and we are going kind of, we are kind of analyzing the kind of critical points that we can find in this function. So the idea was to analyze the number of in this case, because these spaces are two-dimensional, we only have a minimum, maximums, and saddle points. And here, for instance, in this case, white dots are saddle points, red dots are maximum, and blue dots are minimum. And similarly, this is for the alanon dipeptide, and this is for the spherical component of the conformational space of cyclooctane. All right, so this is a summary. Maybe I just will say that, well, this is a new construction of a molecular graph, which allows us that to, to consider topological and geometric constraints. GPI is a generalization of the CNPI group. And maybe the most important thing is that we have showed that geometric and topological data analysis provides with tools that can be adopted to the study of topology, of the topology of different notions of conformational spaces and their energy landscapes. And I think that's it. And just wanted to share a picture of my collaborators. Thank you very much.